All right, gang, STAT1150, brief video on intro to probability and odds. So let's do it. Probability values, key concept, are always going to be between 0 and 1. So the closer the value is to 0, it indicates that the event is uh, very rarely going to occur. And when the values are closer to 1, it means that the event is almost always going to occur. Probability values must, let me repeat that, must be between 0 and 1 inclusively. A probability of 0 means it's never going to happen. A probability of 1 means it's going to happen every single time. Uh, if you calculate a probability and you get something like 1.7, and then it's impossible. You've made a calculation error. Again, can't be higher than 1. If you get a probability that's negative, then you've made a calculation error. It can't be below 0. Now, basic ideas in probability: an event is a collection of results or outcomes, usually for which you want to calculate a probability. A simple event is an outcome that can't be broken down in any simpler components. So this is going to be much better illustrated through an example. And super important, the third bullet, the sample space is just all possible outcomes. So simple events and sample spaces. Let's say we're talking about giving birth. So the procedure, the first example is single birth. An example of an event may be what's the probability of having a girl? The sample space is all the possible outcomes. So boy, girl, only possible outcomes. If we have 3 births, an example of an event may be, boy, 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 right? So what's the probability of having 3 births and having all boys? Actually, a buddy of mine had 5 children, and he had 5 boys. So B, 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 B. Pretend I said 5 Bs. So anyway, the sample space would be all possible outcomes. So there could be boy, 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 girl, and so on and so forth. So what's an example of an event for 2 births? What is the sample space? Give you just a second to think about that. So an example of an event, wow, that's hard to say, of an event for 2 births would be girl, girl. The sample space would be all possible outcomes, which could be a boy, boy, girl, girl, boy, or girl, girl. So the probability, as we'll see in just a second, of getting, having 2 births and having a girl, girl would be 1/4, because there's one event that aligns with GG out of 4 possible outcomes. And that's what we intend to do in this video, in this lesson, is just to keep probability very, very simple. I mean, we teach multiple classes on probability here, and we teach one class in our graduate program. So probability can get very complex, but that's not what we're doing here. We're trying to keep just at least provide an introduction to you for the simpler, more fundamental concepts of probability. So we know what an event is. An event is just something that we can take from our sample size. However, a simple event is an event that can't be broken down any further. So the result of a girl is a simple event, and the result of a boy is a simple event. But with 3 births, the result of 2 girls followed by a boy is a simple event. But just by saying we want an event of 2 girls and a boy, that is not a simple event. It's a simple event when we say that it's going to be 2 girls followed by a boy, because we know that has to be GGB. But if we just say in general it's just 2 girls and a boy, well, then it could be BGG or GBG. So it have more than one a way of representing that. So it can be broken down further. So rolling a single die, the outcome of a 5 is a simple event. Rolling a die, the outcome of an even number is not a simple event, because it could be 2, 4, or 6. So simple event, there's one particular outcome only. It can't be broken down any further. So again, not a simple event with 3 bursts. The event of 2 girls and a boy is not simple because it can occur multiple times. Again, 2 girls followed by a boy is more specific, which would be GGB, and there's only one outcome. That would be a simple event. So tattoo that one to the brain. Some notation, P, capital P, just denotes the probability of something happening. A, B, C, D, E, F, G, whatever, denote specific events. So if we say the probability of Z, so P parentheses Z, or as I put there, P parentheses A, just denotes the probability of the event A occurring. Again, overview when things are important. Well, it's all important, but when things are really, really, really super important, I tend to be slightly repetitive and maybe redundant. But I want you to see that again, probabilities have to be between 0 and 1 inclusively. Numbers closer to 1 means it's very, very likely going to happen. Numbers closer to 0, very, very unlikely. If we have a probability of 1, again, it means it's going to happen every single time. If we have a probability of 0, it means it will never happen. Probability of 0.5 means flip a coin, 50-50 chance, equally likely. Now, in rounding probabilities, I typically like to round probabilities in decimals. I think they're more easily understood. But, you know, putting them in a simple fraction is also perfectly fine. Law of large numbers. Now, this is interesting because I used to go to Vegas a lot, Las Vegas. I think I've been there 19 times. No, actually, I think I've been there over 20 now. But anyway, the last couple of times I went, I didn't even gamble. But when I used to go, because of my background, which is obvious, I used to play a lot of blackjack and roulette. Well, roulette's the dumbest thing you can play. Well, it's not the dumbest, but it's just not that good. If to go to Vegas. So anyway, circling back here, the law of large numbers just says if a procedure is repeated again, then the empirical, what we see experimentally, what we observe, will start to approach the theoretical. It's kind of like flipping a coin. You know, if we have a fair coin with, you know, head, tail on one side, what's the probability of getting a head? Well, it's 0.5. But if you flip that coin, I've seen this happen. I've actually seen someone flip a coin 4 times in a row and get 4 tails. Well, that would lead you to believe that maybe the coin's unfair, and it could be. There are tests for that. But let's say again, the coin is fair. What the law of large numbers tells us is don't put too much stock in short-term experiments. Law of large numbers tell us if we repeat this over and over and over and over and over again, what we begin to see will start to approach the theoretical expectation. So if we flip the coin over and over and over, even though it may be tail, 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 tail the first 4 times, then that's going to start leveling out, and we're going to see more an equal distribution of heads and tails. It's really an interesting phenomena in playing roulette. And we'll get into roulette more in just a second. So an example, a Pew Research Center survey randomly selected some people and asked if they have ever been or ever seen or been in the presence of a ghost or ever seen a ghost. 366 said yes, 1,637 said no. Personally, I actually think I have, but more about that one later. So based on these results, find the probability that a randomly selected adult says that they have seen or been in the presence of a ghost. So the solution is simple. If we have 366 yeses and 1,637 nos, then add those two together, we have 2,003 total responses. So to find the probability of a randomly selected person saying yes, we would take the number of yeses, 366, divided by 2,003, the total number of people, and we get 0.1. 0.183. So we would say that there's a 0.183 probability that a randomly selected adult from the survey has seen or been in the presence of a ghost. Now, the complement is just, in the previous example, would be the event of not seeing or being in the presence of a ghost. Almost said goat. Oh my goodness. Well, this is denoted by A. You can see me circling right here. It's denoted by A with a line over it. So if we have an event A, then A with the line over it denotes not the event A. So in a Pew Research, again, the survey of 2002 randomly selected adults, let's say that 1,782 of those said that they used the internet. Find the probability that a randomly selected adult does not use the internet. Well, there's two ways to do this. The first way is just to understand that the probability of A plus the probability of not A always has to be equal to 1 if the two are the only possible outcomes and they're mutually exclusive. So what I could do there is I could just take 1 minus the probability of using the internet and get 0.110. The second solution is just to find the number who do not use the internet. So if I know that I have 2002 total and 1782 use the internet, then I can subtract 1782 from 2002, get 220. And those people do not use the internet. So I can take 220 divided by 2002, and I get the same answer. Not intending to make this complicated, just intending to show you different approaches, because it depends on the nature of the problem, the approach that's easiest for you. So probability review, again, probability is an event that must fall between 0 and 1. And, you know, the rest of the stuff there I'm not going to read to you because I'm just not, because it's right there. So let's get into odds. Odds are really misunderstood. I was actually refereeing a math competition one Saturday morning, and there was the biggest fight over odds because some high school teachers didn't understand odds. They were confusing it with probability. So it's not that hard. So let's just dive in and see what is all about odds. So the odds of an event A, just a general event A, can be found by taking the probability of A divided by the probability of not A. Again, the total sample size here, the total number of respondents, the total, isn't relevant in odds. Again, it's the probability of A divided by the probability of A not occurring. So let's say the probability of some event is 0.212. Then what are the odds of A? So it will be the probability of A divided by the probability of not A. So it would be 0.212 divided by 1 minus 0.212, the way we find the probability of not A. Doing the arithmetic, we get 0.212 divided by 0.788. So the odds would be 0.269. Probability of an event A is 2.12 again. What are the odds of not A? Oops, I got a typo. That should be switched. This should be the probability. The line should be over this A and not that A. First mistake I've ever made, and you guys got to witness that, right? Yeah, right. So anyway, but from here over, this is all correct. So the probability of not A would be 1 minus 0.212 over the probability of A, which would be 0.212, and we get 3.717. Another way we could do that is just take the inverse of the probability of A, which is just 1 divided by 0.269. We get the same thing. That's typically the way I find the odds of a complement, is just to find the odds of A and then just take my answer and just take 1 divided by that, and I get the the odds of the complement. So I've been talking a little bit about roulette. This is what a roulette wheel looks like. There are 38 slots in the wheel. There are 18 reds and 18 blacks, and then these two greens, double zero and zero, are kind of what shifts the odds to the house. Ever fly into Las Vegas? You notice that they've got these big, what look like $1 billion, just absolutely gorgeous casinos and hotels, resorts. It's really impressive coming in. The reason they can build all that fancy stuff is because every game has an odds that shifts to the house. And in this game, the odds are the two green zeros. So if you bet on red in roulette, what's the probability of winning? Well, if I count all the reds, I can tell you right now there are 18 of them. And if you count all the slots, I can tell you right now there are 38 of them. So there are 18 reds out of 38 possible outcomes. We'll turn you guys into a bunch of gamblers here. Hopefully I don't, because you're more than likely you're going to lose money if you gamble out there. So the probability of winning would be the 18 divided by 38, which is 0.474. Notice that's less than 0.50. That's called the house odds, right? It's the reason they can build those big old fancy casinos. So the odds of winning would be, again, the probability of winning divided by the probability of not winning. So 0.474 divided by 0.526 is 0.901. So the odds of winning are about 90%. But circling back to the law of large numbers, what can happen? I mean, I've actually seen, I forget whether it's red or black, but I actually saw one time 7 reds or 7 blacks, one of the two, 7 of one color hits in a straight. What's the odds of that? What's the probability? That's very, very low probability. That's not supposed to happen, but it did. I saw it. My point is, if you just play this game over and over and over and over, about 47% of the time you're going to win, about 53% of the time you're going to lose. So what are the odds of losing? Well, the odds of losing would be the probability of losing is 1 minus 0.474, so equal 0.526. So the odds of losing would be the probability of losing divided by the probability of winning. So the odds of losing are 1.111 times. So anyway, if you gamble, gamble responsibly. All right, the summary of odds. If the odds are greater than 1, then the odds are in your favor. If the odds are less than 1, then the odds are against you. If the odds is 1, well, I should say if the odds are equal to 1, then it's a flip of the coin scenario. You know, winning and losing equally likely. All right, gang. That's all I have. I enjoy probability. I think it's again, we don't get into it much in this class, but we need to set the stage for probability. I'm sorry, we learn probability to set the stage for normal distributions, sampling distributions, and p-values when we get into these tests of inference. All right, gang. That's all I got. Take care.